Good afternoon, everyone. My name is Guan-Wen Chen, and I am from National Yangming Jiaodong University. Today, I'm going to give a talk named as Extracting High-Definition Map Information from Aerial Images. This is my outline. First, I will introduce the motivation and purpose of this study. Then I will give a brief definition of the format of the standard Open Drive and the semantic segmentation model we used. After that, the system proposed in this work will be explained, and the aerial dataset collected by ourselves. Experiment results will show the performance about the detection and post-processing results compared to the ground truth. Finally, I will give a short conclusion and future work to our study. The Society of Automotive Engineers defines 6 levels of driving automation ranging from 0 to 5. These levels have been adopted by the U.S. Department of Transportation. In the near future, self-driving vehicle will focus on level 4 and level 5. Therefore, high-definition map, which is HD map, is required for autonomous vehicles. Different from traditional digital map, HD map is a highly accurate map used in autonomous driving, containing details not normally present on traditional maps. Such maps can be precise at a centimeter level and contains the data with 3D information in land level. At present, some standards are published for constructing HD map. OpenStreetMap is a user-generated street maps. It allows people to upload the HD map information like Wikipedia. Navigation Data Standard, which is NDS, is a standard of navigation database format and is used in navigation devices. NDS defines the database structure to store the HD map information. OpenDrive describes the data exchange format in XML file, and various information in the traffic network can be changed to OpenDrive format. Due to the various 3D information needs to be described, it is a lot of labor work to construct a complete HD map. For example, in an intersection, there are several different kinds of road markings on the surface. Also, the symbol signs and the traffic signals are need to be saved in HD map. An unmanned aerial vehicle, which is UAV, also known as a drone, is an aircraft controlled by human to execute the task remotely. Most UAV are carried camera to record the aerial video. Because of its flexible control in the air, it is easy to collect traffic images by UAV. Therefore, to reduce the labor work of constructing HD map, our goal in this study is to create road information automatically. The road markings information will be extracted from aerial images recorded by the camera on the UAV. A deep learning model is used to detect the road markings on the road surface. Then the information followed by OpenDrive format will be drained after the post-processing. Also, a web-based edit tool is developed in this study to modify and export the XML file. This is our proposed system. An aerial image is as an input of DeepLab v3+, which is a semantic segmentation model to detect road surface and road markings separately. Then the detection results will be transformed to OpenDrive format in the post-processing. The web-based UI will visualize the results and can modify and export the XML file. XODR file is the basic data exchange file of OpenDrive and is written in XML, which is Extensible Markup Language. The structure of XODR file is divided into 5 parts, which are header, junction, row, controller, and station. In this study, we focus on the information on the row surface. Geometry describes the parameters of the reference line of a road, and 3 types of linear equation can be used. Object is the region markings or other objects on the road. Link is used to illustrate the correlation between the roads, and so is lane link. Width is recorded the lane width compared to the reference line. Row mark is the information of the line on the road. Reference line is the basic element of a road. A lane will be described based on the reference, and the features like signals that are placed along the road. A reference line of a road can be divided into several segments to follow the linear equation from OpenDrive. For example, 3 types description of a reference line are depicted. In a attribute, ID is the object ID, and S is the start position, XY is the start position of the initial coordination. HDG is the start orientation. The length is the length of the element's reference line. And in arc line, the curvature describes the constant curvature throughout the element. The spiral has 2 curvature attributes, which is curve start and curve end. Deeplet v3+, which is a semantic segmentation network, is introduced to detect the row region and markings. Every pixel in an image will be labeled by the network and marked as different category. For example, a human will be marked as skin color, the horse is pink, and the dog is purple. Proposed system in this study is mentioned earlier. All the intersection from an aerial image can be transformed to the XODR file by the system. In a deep learning model, we modify the network to predict row region and row markings in an image. After that, a sketch of an intersection can be visualized by combining the 2 results. In a post-processing part, we need to extract the lines on the road and transform those lines to geometry description. In this instance, there are 1 yellow double solid line, 2 white solid lines, 1 stop line, and 2 red solid lines. The length of each line will be calculated in pixels. Then the reference lines needs to be assigned. Usually, the center line on the row is marked as the reference line to divide the lengths in different directions. In this case, the yellow double line is marked as the reference line. The start point can be any position of the reference line. To simplify the line in question, the end of the line is defined as the start point, and we take the end point near the intersection as the start point. The rest of the lines is described as the lane width to every point of the reference line. When the information of all the rows on the intersection is finished, we need to generate the virtual lanes in the intersection and define the junction of each lane. In OpenDrive, the gap or overlap between two lanes is not allowed. Therefore, the virtual lane can be cut into several lane segments to link the lanes, and different geometry description can be used to illustrate different types of the virtual lane. At this moment, the row markings information of an intersection is completely described and transformed to OpenDrive XODR file. A web-based tool is developed to visualize the transformation results. If there are some errors in the result, the tool can modify the file to be more accurate. Finally, the XODR file can be exported by the web and saved to PC. The dataset is the intersection area image taken by UAV. There are totally 1,670 images with annotation, and the dataset is divided into training set and testing set. We defined 18 categories of annotation used in the intersection, such as lines, crosswalk, and direction signs in different types. In our experiment, IOU and PA is introduced to evaluate the performance. IOU is the intersection of a union, and PA is the pixel accuracy. We evaluate the performance of each category of row markings between the div lab v3 plus prediction and the ground truth. And the MIOU is 84.3% and MPA is 93.5%. Also, we compare the errors between the ground truth and the results after transformed to OpenDrive format. In Taiwan, the requirement error of 2D information in HD map needs to be under 20 centimeters and under 30 centimeters in 3D information. In our conclusions and future work, the proposed system can detect HD map information from aerial image recorded by UAV using deep learning model, and the OpenDrive file can be generated by post-processing method. In our experiment, the MIOU is 84.3%, MPA is 93.5%, and the average error is 12 centimeters. And a web-based tool is developed to edit and export OpenDrive file. In the future, 3D items on the road such as traffic signals, regulatory signs are introduced to have a complete 3D information of the OpenDrive file. And the detection model needs to be optimized to detect small lines on the images to meet the error requirement. Thank you for listening.